Have you ever wondered what a number even is? It's not a very straightforward concept, but it's something that's actually worth considering. So in this video, I would like to explore a very interesting paradox with the goal to hopefully inspire you to think differently about numbers. The hope is that in turn, this will expand your mathematical curiosity and maybe also your understanding. Now, to explore this main idea, let's consider the following scenario. There's a table in a room, and on top of the table sits a ball. Now, what we can do is we can apply a little bit of force onto this ball, and this will give it a little push. As we push the ball, it will move, and something really interesting will happen when we get close to the edge. Push the ball hard enough, and it will reach this point of no return, after which the ball will fall off the table, and gravity will take over. However, just before the ball falls, something really interesting is happening. There's this state where the ball is on the table, and after that there's a state where it's off the table. And you might be able to imagine this infinitely thin line that sits at the edge of this table. If the ball is on the left side of this line, that means that the ball is still on the table. But if the ball touches the line, that's where it starts falling. And because it's the moment that the ball is on this line that there's a big change, then we can look at this line and say that this line represents a tipping point, where on the left nothing special is happening, but on the right there's a point of no return. And this phenomenon of a tipping point was very interesting to me when I was young, because it's not just happening to a ball that's on the table, it's something that tends to appear in a lot of places. As another example, let's suppose that there is a cup of tea that's also on the table. Then, if the cup of tea were to fall, there's a chance that it might break. Now, the cup breaks if it falls from a height that is too high. And also here, I hope you might agree that there's a tipping point. If the height is high enough, the cup will break, but if it's small enough, then there's no problem. And where this tipping point exactly is, and how close we might be able to get to this tipping point, that is a concept that I thought was super interesting. So let's explore this tipping point mathematically. The idea is that by looking at this problem with maths, we might more easily be able to learn a lesson from it. So let's be formal and let's define a place on the table where the ball starts. And let's also attach a number. Let's say that on the number line, the ball starts at 0. And let's then also say that the ball starts falling if we ever hit 1 on this imaginary number line. We now have a distance between where the ball starts and where the ball starts falling, and defining this makes the situation a little bit more tangible. Because what I can do now is I can move the ball to its starting point, and from there, I can move it to the right and keep track of the total distance that it has traveled. And I'm calling this distance traveled x for now, but the main point is that as the ball moves more and more to the right, the distance increases. But we are going to have to be careful with the amount of distance that the ball can actually travel. The idea is that the ball can move very close to this tipping point that we have over here, but we wouldn't want the ball to go over the tipping point. The nice thing about defining the problem this way is that it makes it a little bit more tangible and also easier to ask interesting questions about this number x over here. The thing that interests me the most about this tipping point revolves around this question of how far can I push the ball without hitting the tipping point? How far can I push something without something breaking? And by defining this mathematically, we're able to rephrase the original question that we had over here and translate it into, what's the largest number that is smaller than 1? Now, this is an interesting point in the video for 2 reasons. One, we have translated an interesting problem into something that's mathematical and perhaps even solvable, but also because this question is actually somewhat involved. Let's look at the question. The question itself is actually already describing a number. Or at the very least, it's describing the concept of one. Namely, the largest number that is smaller than 1. But it's likely that something inside of you is thinking, well, a concept is nice, but a concept is not enough. Instead of this abstract concept, you're probably more interested in a familiar representation that makes it easier for you to reason about what this number actually represents. So let's talk about numbers, and the difference between a concept and a representation. Now, the best way for me to explain the difference between a concept and a representation is to show you some numbers that you might initially not expect. So, here's a few. Now, these numbers right here, they are genuine numbers, but they're often referred to as Roman numbers. And the reason for this is that this is the way that the Roman Empire used to use letters to represent numbers. You can translate them into our more modern number system. Note that both number systems are capable of referring to the same number. For example, IV as a number is the same thing as 4. It's just a different way of writing the same number down. So the way that a number is represented is different than what the number conceptually means. And even our own modern numerical system allows for multiple representations of the same number. For example, I can add a decimal. Now, as far as the mathematics is concerned, adding a dot and a 0 doesn't change the meaning of a number. It's just a different way of writing it down. Now, I would argue that this way of writing down a number isn't necessarily practical, because the same number can also be represented in this format, which would save a lot of ink and removes unnecessary information from your retina. But the main point is, we are able to represent these numbers that are perhaps the same in different ways. This whole idea of representation should be taken serious, though. It's not merely an esoteric discussion. The choice of the representation of a number has some really serious consequences. There's a reason why we're no longer using the Roman representation for numbers. And to give a simple example, let's take the number CXXVIII. Does this really feel like a convenient representation of a number to you? Or do you also experience that conceptually there's a lot of translation happening in your mind before getting a clear picture of what the representation actually means? The thing with Roman numbers is that they are harder to reason about. But it's not just that, they're also a lot harder to reason with. And to point out why this is true, you only have to consider translating in the other direction, from our modern system of numbers back to the Roman ones. So let's try and do that and see what happens. Let's say that we want to translate the number 0. Well, the Roman numbers don't have a representation for that. And it's not just that, also negative numbers aren't represented. And this has serious consequences. Just think about it. What would numbers be like if we didn't have 0 as a concept? Because you have to recognize that that circle that represents 0 carries a lot of meaning. It's not just a way of denoting nothing, it also denotes decimals and higher powers of 10. And in fact, if you have a number system that's represented this way, then you also are able to achieve new notation that builds on it. If you think about these powers of 10 this way, it comes to no surprise that eventually this notation made its appearance. If we take the number 10,000 for example, we can say, well, that's 4 zeros, so let's rewrite that as 10 to the power of 4. Not only does this save a lot of ink, but it's also a way of reasoning about numbers. And just consider how much of this ability to reason is contributed by the notation. You're not able to do any of this with Roman numbers. But there's more. If you look at how naturally our modern number system is able to deal with these powers of 10, it should be less of a surprise that related mathematical concepts are also possible. You might be able to consider powers of 10 to be a function now. And understanding the power of 10 will likely also allow you to discover the idea behind a logarithm. And similarly, it also feels more natural that conceptually, you'll be able to stumble upon the idea of a square root. But one of the main lessons here is that you're only able to think these thoughts, and you're only able to reason about these concepts because we have a convenient way of representing numbers. If you have a horrible representation of numbers, like these Roman numbers, then it's much harder to think about them and to reason with them. Just think of all the scientific discoveries that this number system is denying you. And to me, this is probably one of the most important lessons in mathematics. Notation really matters. If you take notation for granted, like some of the Romans did, then effectively you are denying yourself the ability to discover many new things. Now, we will see that this representation of a number becomes very important in a moment. For now though, let's think back of our original exercise, because we were looking for this number, namely the largest number that is smaller than 1. And the key point here is number. We are going to explore how we might be able to represent this particular number. But it also means that we have to maybe reason about it some more. So as a thought experiment, let's consider this number that I've just written down, 0.999. Is this the number that we're interested in? It might be easier to explain if we zoom in a bit. I hope it's clear that this number is not the number that we're interested in. And the reason is, there's a little bit of space left between this gray line that represents where the ball is, and this black line where it starts to fall. So that means that there's still a little bit of wiggle room, which means that we can move the ball further to the right. So how about this? I'm going to be making this number over here bigger, and then we'll see if we actually get closer. And it's a little bit closer, but it feels like there's still some wiggle room. So let's do this again. And again, we are getting closer, but still I can make the argument that there's a little bit of space still left. So maybe I need to follow a different approach. Maybe this is the number that I'm interested in. It's 0.9 all the way down till infinity. This seems to be like the number that I'm interested in. The only downside is that I don't have enough ink to actually write this number down. So it feels like there's something that we need to do here with regards to notation. So here's a proposal. Instead of writing down all these 9s, we are just going to assume that if I put a bar over the 9 like so, that it indeed goes on forever. Again, I would like to highlight how convenient it is that we have this representation of a number, because it allows us to be somewhat flexible in notation, which gives us a lot of flexibility in things that we can communicate. So I suppose there you have it. I could argue that this is the largest number that I can come up with that theoretically should still be somewhat smaller than 1. But there's something about this number that is making me wonder. It might just be that this representation of the number is hiding the true nature of the number. If only we could rewrite that number into some different form, we might be able to learn more. Now, one thing that you can do, because it's still a decimal number in many ways, is you can apply arithmetic to this number. For example, I can definitely say that this number is 3 times this number. And I can also say that this number over here is 9 times this number. And the ability to do this arithmetic does make it feel more tangible, but there's something still telling me that we're not necessarily closer to understanding what this number is. We've merely written it down in a way that saves ink. So I'm about to introduce a new representation of a number, and I'm going to apply it to understand this number a bit better. So let's go back to the drawing board to talk about numbers once more, and I'll use this number line as a vantage point. If I consider the length of this number line, it's starting at 0 and ending at 1, then I hope that you would agree that the length is equal to 1. And what I can do is I can say, well, let's cut that distance in half. This will give me two parts, this left side and this right side, and the length of each part will be 1/2. That's exactly what this fraction represents. It's saying, hey, we've got this unit that's equal to 1, and we are dividing it in two pieces. One really convenient property of this is that we can always say, well, 2 times 1 divided by 2 is equal to 1, by merit of arithmetic. Another thing that's convenient is that 0.5 in this case has a correspondence with a half. This fraction over here can also be represented as a decimal number. But let's consider some more fractions, because if we can divide by 2, we can also divide by 4. Again, 1/4 has a correspondence with decimal numbers, and once more we get this convenient property that 4 times 1/4 is equal to 1. And we can do this again. We can divide 8 times. We now get 8 of these fractions, and again we have this wonderful correspondence with a decimal number. Now, what we can also do is we can divide by 10. And this is where the correspondence becomes even more striking. The relationship between the fraction that you see here and the decimal that you see here, there really is a direct correspondence between 1/10 and 0.1. The length from one decimal line to the next one is exactly 1/10. Another interesting way of looking at these fractions is to say, well, we are looking at a equal split on the number line. Each segment is 1/10, and that's what it means to divide by 10. We could give the first 1/10 to person number 1, the second 1/10 to person number 2, etc., etc. By redrawing this slightly, I hope that you agree that I can rephrase what it means to divide by 10, a way that has little to do with decimal numbers. Dividing by 10, put another way, is making sure that each person gets a piece of equal length. And this is exactly what a fraction represents. However, there are also fractions where this natural correspondence with decimal number diminishes. For example, what would happen if we divide by 9? Well, dividing 0.9 amongst 9 people, that's pretty easy. But what do we do about this little bit that's left? That's a little bit unclear. So let's explore what 1 divided by 9 might be if we were to represent it as a decimal number. The first thing that I can do is I can split the problem up into two pieces. As I said before, dividing 0.9 by 9, that's relatively easy, so I can make note of that, and then worry about this part maybe later. I can split up 0.9 in 9 equal segments that are each 1/10, and this allows me to say something like 1/9 that seems to be 0.1 plus something extra. So that means that I can consider part of the number line dealt with, and I can expand the part that I still have to investigate. This segment that I have over here is the part that I still need to split up to accommodate for this extra part that I've mentioned up here. So again, I can have a look at what I have. I've got a new number line that starts at 0.9 and it ends at 1. And you'll notice that again, this number line has 10 equal pieces on it because that's what decimal numbers dictate. And I can forget about the part that I already dealt with, and I can zoom in on this. However, I seem to be hitting a similar issue. Where before I had 9 parts of 1 over 10 each, I now seem to have 9 parts that are 1 over 100 each. But okay, let's say that I take my lesson learned, I'll add this 1 over 100 here, which means that now again I have dealt with a large part of this new number line, and I can say, well, there's still something extra, and that extra bit can be unraveled by investigating this final bit over here. I hope you recognize by now that we seem to be repeating ourselves. Because the number line has these decimals that I'm using as a reference, I hope you agree that I can keep doing this, well, forever. This will go on and on and on. And I hope you would agree that I can zoom out and I can repeat this, and I can keep repeating over and over. But it seems that if I want to have this number that's 1 divided by 9 be represented in a decimal format, that I need to apply a trick that we saw earlier. I need a notation. Namely, I need this notion of this bar, which means that this number is going on forever. And this is a pretty amazing observation, right? Fractions are able to capture this idea of infinity, something that decimal numbers inherently cannot do unless we introduce a specific notation for it. So maybe decimal numbers are like Roman numbers. Just like Roman numbers were limited in what numbers they might be able to represent, we also see here that decimal numbers have limits. A fraction seems to capture this infinity after a decimal way more naturally than decimal numbers do, and that makes them easier to reason with. And reasoning with numbers is exactly what we want to do. So let's now go back to our original problem. And so here we are, back again. We are looking for a distance that the ball can travel that's as big as possible, but not so big that it crosses or hits this tipping point that we defined earlier. With that in mind, we came up with this number, namely 0.999 till infinity, that feels like it should represent this distance that we're indeed interested in. Now, we weren't satisfied with this number, so we figured we should explore it, and that's how we determined that we can also write it down this way. However, we also just discovered that this 0.1 till infinity expression can also be written down as a fraction. But if we now follow the arithmetic, it seems that 9 times 1 over 9, that's 9 divided by 9, and that is equal to 1. Now this is an important moment, because there are 2 things happening. For starters, it really does turn out that by translating a number through different representations, we're able to more meaningfully think about the number. And the other thing worth noting is that we seem to have stumbled upon a paradox. The way that we came up with this number is we wanted to prevent this wiggle room. And that's why we said we are going to keep increasing this line, but only in such a way that it never hits this one. And the way we did that is we came up with this number 0.999 till infinity in an attempt to close the gap closer and closer and closer. But it seems if we actually do this all the way down until infinity, that the number that we came up with is actually exactly equal to 1. And that's also to say, not smaller than 1. But maybe there isn't a paradox in the mathematics that we've just discovered. That seems fine. Instead, maybe there's a paradox in the question that we're asking instead. You see, we are asking a question here about a number, but the question is also making an assumption, namely, that this number even exists in the first place. In this video, we've been talking a lot on how we might be able to represent a number. And we've shown how the concept of a number can be rewritten into different representations, and that this may actually help you understand the true nature of a number. But that doesn't mean that every concept that we dare dream of actually represents a number that exists. For example, let's say I was asking you about a number that is less than 1 but greater than 2. Then you would be completely correct to call me crazy, because we're asking about a number that doesn't exist. And the same thing seems to be happening to our question here.